All right, this is Mr. Hulsey of 8 Squared Sufficiently Understood Science, and today we're going to be taking a look at how Earth's rotation and revolution occur, and this will eventually lead into our discussion about how Earth's seasons work. So, rotation is the spinning of the Earth on its axis. So right here we have the axis of the Earth. Um, Nice straight line, if I can ever draw a straight line, right through the Earth, right there. And you'll notice it's not completely up and down. You would expect that the axis would be a perfect little line, but it's not. As a matter of fact, the Earth's axis, we're going to discuss this quite a lot, is tilted by about 23.5 degrees. And so what we're going to be doing, we're going to be discussing this. So the Earth's rotation, once again, is the time it takes for, let's say, right here in Africa, to go around one time. Okay, so the Earth's rotation is 24 hours, and so the Earth is going about 24,855 miles in 24 hours, or roughly 1,038 miles per hour. So as the Earth spins counterclockwise. So if you can imagine a wall clock up here, 12, 3, 6, 9. A normal clock will move in this direction, going from 12 around. Okay. Now counterclockwise is moving in the opposite direction, where it's going from 12 to like 3. And so that's how the Earth is spinning. If you can imagine this dot right there as the axis. So as it is going, it's going in a counterclockwise motion. Most of the planets in the solar system are going to do that, except for Venus. So we're going to be moving from left to right. Okay, moving from left to right. So this rotation is responsible for the occurrence of night and day. Without the rotation, well, I say that, but that's not 100% true. Revolution does play a part in if we didn't have a rotation, but for all intents and purposes, rotation is responsible for the night and day cycle, that 24 hours where we have light and darkness during that time. So our rotation is responsible for that. So some evidences for Earth's rotation. This is actually one that we can find here in Houston. This video is actually from the Houston Natural History Museum. Is Foucault's pendulum. This was made in 1851. So there's no force actually acting on this pendulum to make it move. The plane of oscillation is actually going around its own axis because the Earth is spinning. So it would continue to swing in the original path, never hitting anything but maybe one or two of these little wooden things, if it weren't for the fact that the Earth is spinning. So the Earth is actually spinning beneath. As this thing is moving, the Earth is spinning beneath this pendulum in a counterclockwise manner. And so as the pendulum swings throughout the day, it hits different pegs. It's pretty wild, because it's kind of going by that whole an object in motion will stay in motion in a straight line kind of thing. The pendulum is staying in a straight line, okay? But the Earth itself is rotating beneath the pendulum. Another is the Coriolis effect. And this is the tendency for objects moving over the Earth to curve away from a straight line. So we move from, west to east and everything like that. So that's why it appears like the sun comes your direction. So if you were to throw a paper airplane from, Houston up to, Chicago or whatever, you expect it to fly a straight line. But the thing, or Nebraska or whatever, in the example. But the thing is, because the Earth is spinning, and it's actually spinning faster at the equator than it is at the North Pole, near the poles higher up, that thing is actually going to curve and land somewhere around there. I think that's Washington, D.C. or Delaware. So
here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
And so the Earth's rotation, we can definitely tell it's there because there is a tendency of an object moving over the Earth to curve away from a straight line, even though we know that an object in motion that stays in motion should actually remain in motion. And so it changes the path as the Earth moves beneath the object. So the northern hemisphere, things tend to move to the right. In the southern hemisphere, they move to the left. So the spinning would be to the right and southern hemisphere to the left. So let's start with a little bit bigger scale. We're going to talk about revolution now. So rotation on the Earth's axis, revolution occurs as the Earth moves around the sun. Okay, so this is our year. So revolution is a year, rotation is a day. So one revolution takes 365 and a quarter days, roughly 8,766 hours, and we are moving at 18 miles every second. Now, I want to take a look at this video that we see right here. First of all, this is a really cool scientific tidbit. You'll notice how the sun's light dims out right here. Boom. That's actually one of the ways that we find exoplanets, is we look for a dip in light around the star that indicates that there's something orbiting it. But that's neither here nor there. I want to focus on revolution. So as we said, the revolution is one trip around the sun. Okay? So one trip around the sun, and that takes 365.14 days. Okay, or 1/4 days, or 365.25 is what I usually say. But I want you to notice something about the axis here. So you'll notice that at all times, the axis, the way the Earth is actually tilted, doesn't change. You see what I'm saying here? This is what's going to be very important in our next lesson. And this is a really good visual. That axis right there, it's the same angle. As it goes around, it's always at that same angle, that 23.5 degrees. The axis doesn't like shift with the planet. So what I'm trying to say is, if the axis, so let's say we have our star, and I'm going to do it in purple for some reason. Okay, and our axis is shifted like, let me switch that color, like that right here. As we go around, the axis will remain like that. It's not going to switch over and be like this on the other side. It's not going to face the opposite direction. The axis is always like that. Now, seasonal constellations are a good evidence of Earth's revolution around the sun, because some constellations are visible at night only during certain seasons of the year, because we're at different locations around our solar system. So as in, you may be pretty familiar with these, like Leo, Cancer, Gemini, Taurus, Aries, Capricorn, Sagittarius, Scorpio. These are those things, your birth signs and stuff like that. That's what those are based off of, is the seasonal constellations that are visible only during certain seasons. Also, another evidence is a little bit more scientific, is parallax shift. So what this is a really good evidence right here, is that near stars seem to shift their position against the further stars. So let's say, for example, in January, so we have all these distant stars in the background. I want you to pay attention to the pinkish star. So in July, right here, all right, when we're in July, we see the star right there, okay? And as we truck our way along around the sun, in January, we'll see the star over here. And you'll notice that the white dots are the same. So our perspective has changed as we've gone around the sun. So this is a big evidence of Earth's revolution, is that things have changed position. And so this is what we call parallax shift. So once again, the Earth's axis is tilted at 23.5 degrees from the vertical. And that's a very important number to know, that 23.5, because in our next lesson, we're going to be talking about how just that degree of tilt is really responsible for all the different seasons that we have on our planet. And so that axis, like I said, is not going to change. So think for a second, have you ever heard the term Polaris? Well, Polaris is the name of a star. It's the North Star. And let's think about this for a second. If the Earth's axis is tilted at 23.5 degrees to Polaris, right? To the North Star, and the axis changed its position. So if it's pointing to Polaris right here, and it went around, and as the Earth spun, the axis spun, by the time we got to the other side, the axis would be facing a different star, and so Polaris couldn't be the North Star. So this is the evidence right here, since we're always pointing towards Polaris at 23.5 degrees. That's our northern star. That gives us evidence that that is actually our axial plane. So we are on an elliptical plane around the sun. Okay, our axis, or not our axis, but our revolution is not 100% a circle. So what's interesting is as we go out here, now here on our shortest area around the sun, okay, which this diagram's a little bit off because really it should be a bit different. But anyway, we actually go faster around our shortest, our closest approach to the sun than we do on our furthest approach. Well, I hope you've learned a lot from this tutorial. Once again, this has been Mr. Holsey for H Squared's Officially Understood Science. Join us next time when we talk more about seasons. Catch you later.